Hello students, this is Mr. McAllen and we're going to be working today on graphical transformations. We're going to work on it in a limited sense because all transformations of all functions work the same way. What we're going to first do is talk about how we shift a function to the left or to the right. Then we're going to talk about how we make a function go up or down. Then we're going to talk about what you do to a function to make it reflect over the x-axis, and then and how you make it reflect. Let me just spell that right. Reflect over the y-axis. We're going to talk about vertical stretching and horizontal compressing. So we're going to do all this in the context of the function f of x equals the square root of x. So in order to move this function to the right or to the left, you would have to operate on the inside of the function. So if I want to call g of x as my function is f of x for comparison, to move this function to the left, I would then take g of x and I would say it'd be the square root of x plus a number. So let's say I want to move it 3 units to the left. So by adding 3 units, it's going to essentially move the function 3 units left. If I want to move the function 3 units to the right, then the function would have to be the square root of x minus 3. Now there's a little trick for how we figure out where exactly that function goes to. If you're going to solve it in your head, you take completely what's on the inside of the function and you set that equal to 0. So when you set x plus 3 equal to 0 and you solve, you get x equals negative 3, and as a result, you know the function is moving left 3. If you beg your pardon, if you do it with the next function and we set that to 0, we will get x equals positive 3, so it'd be 3 units to the right. So we can analyze this with Desmos, and I'm going to bring up Desmos just so we can play around with that parameter, and then we'll do the up and down case. So when we go to Desmos, to Desmos, we'll launch the calculator. I'll put in f of x is equal to the square root of x. That's my parent function. G of x is equal to the square root of x plus 3. Notice it moved to the left by 3. H of x is equal to the square root of x minus 3. Notice it went 3 to the right. Now, just to show you another thing you can do with Desmos, is if I made this a parameter, let's call that b, it would ask me for a slider. And then having a slider, see right now b is at 1, that means 1 unit to the left. But if I increase it, see how it's moving to the left by whatever value b becomes. And likewise, if I make it negative, it's going to move to the right. So here it's at negative 3, exactly on top of the other function. Now what about moving the function up or down? Up or down is an easier case to figure out. In order to move the function up, if we're working with f of x equals square root of x, I'm going to just show that little line there that the radical ends. If I add to it 3 on the outside of the function, so add 3 on the outside, that's going to be up 3 units, because I'm basically adding 3 to every function value that the normal function started with. And I should really change this to g of x, because my original function was f of x. G of x will be root x plus 3. H of x will be root of x minus 3, and that'll move it down 3 units. So, for x-axis movement, okay, that happens on the inside of the function. For y-axis movement, it's on the outside. To demonstrate this with Desmos, Desmos is very clever. The way the it's so mathematical, Desmos. I can actually take those functions we just looked at, and I can, for example, I'm going to turn off, or I'll just, let's just say I have f of x up here. If I do f of x minus 3, do you notice it moves it to the right by 3, that orange function? If I operate on the inside of the function, say plus 3, it moves it to the left 3. If I work on the outside of the function, I do plus 3. Notice it goes up 3, and minus 3, the function goes down 3. So Desmos is very versatile in showing you exactly how these transformations occur. So another thing is if I do two movements at the same time. Let's say I do f of x plus 3 on the inside, and I do plus 4 on the outside. It doesn't like add 3 to the 4 because it has to work within the function first, move it to the left by 3, and then it moves the function up by 4. So let's take a look at our notes again. So the next thing on the list, let me just check the sound, make sure I'm testing here. Okay, we're into 6 minutes. So the next thing on our list was reflecting over the x-axis and reflecting over the y-axis. So this is done very easily with function notation. So if I have a function, if I want to reflect, let me spell that right. I have trouble spelling reflecting today. Reflecting over the x-axis. That's done by if I have f of x, if I put a negative in front of the function, that will reflect, there we go again, over the x-axis. If I put a negative on the inside of the function, that will reflect over the y-axis. Now, an easy way to see this is, let's say I used the square root of x because it shows this pretty easily. So if f of x is equal to square root of x, I could either do it one way, where I do g of x is equal to negative root x. I put the negative in front of the function. See, in front of the function, that would be an x-axis flip. If I want to flip this function, the square root function, over the y-axis, I would put a negative in front of the x inside of the function. So that would be a y-axis flip. So using Desmos, we can show this using function notation or by operating on the function itself. So let me just get Desmos back up on the screen. And I'm just going to erase these functions so we don't have to worry about the translations anymore. So there's f of x. If I say h of x is equal to, if I just even put h of the negative in front of the function, and I'll put like square root of negative x. As you can see there, it reflected the function over the y-axis. If I put the negative in the other spot outside the function, notice it flips it over the x-axis. I can flip both axes at the same time. Pretty neat. I can also demonstrate the same point with if I take the function as it was written, and if I have f of x given to me, I can do f of negative x, and notice that does a reflection as well. Or I can put the negative in front of the function notation, and I get the equally same result as if I put the negative in front of the original function. I can do both at the same time and get both flips. Again, Desmos showing its versatility with function notation. Okay, so the last item on the agenda was showing horizontal stretching, vertical stretching and horizontal compressing. So if I have a function f of x that equals the square root of x, and I want to do vertical stretching, I would put a multiplier in front of the function, so let's say 3 times root of x, would result in a vertical stretch by a factor of 3. If I put the 3 on the inside, okay, this would be a horizontal compression factor of 3. Let's check it out on Desmos just to verify what I'm showing you. Remember, in order to understand this, you need to know what vertical and horizontal are. I know I'm over 10 minutes, but be patient. This will be worth the wait. So I'm going to do g of x is equal to the square root of x, but I'm going to put the 3. Notice how the two functions are on top of each other. I'm going to put 3 in front and see how it stretched everything up by a factor of 3. If I did by a factor of 2, you'd see it's just double the existing values. If I did a 1/2, you'd see that it shrunk it by a factor of 2. Now, I'll just leave that as a 2 to show a stretch of 2. Now, what if I put the 2 on the inside of the function as a multiplier to the x? So h of x is equal to square root of x, and I'm going to put a 2 on the inside. Now this will compress it by a factor of 2. It squeezed the function, let's say 10, or let's say 5. It's basically squeezing the function on the x-axis, making it compress so it actually looks like you're pushing it from left to right, like an accordion. Like imagine if this was a marshmallow, right? And you took that marshmallow and you squeezed it from left to right, it would become thicker in the middle. So let's say that's 3, 4. Heck, I could put an a here, and I could make that a slider, so we could slide the value. So you can see how it's compressing it on the x-axis. Now, a compression on the x-axis looks very similar to a vertical stretch. Let me put, I'll put an A here. And notice when A changes for both the red, and let's just change this function to we'll change it to orange. Okay, when I change the A value, notice both are behaving the same way. But A is behaving like it's stretching much farther than the blue one's compressing. But that's because it's a square root function. Anyway, hopefully this has helped you understand like what a vertical compression value would be. That would be the value out in front, where the horizontal compression would be. I hope this video has helped you understand some basics about transformations, and I look forward to hearing your comments and questions in class tomorrow. Thanks for your patience in watching the video.